Okay, I hope you already watched the introduction video for this course. Now we're going to start going through the course book. So I trust you have already downloaded the course book from the Google Drive folder. If you haven't, please do so that you can follow along with what I'm going to say today. So I'm first going to go through in this video, we're going to go through chapter 1. So chapter 1 is called Research Methods. So the learning objectives for this chapter are to understand what theory and model are, to understand Occam's law, and to understand the different types of random variable. So we're going to start with a very fundamental question. And that question is, what is research? So if we claim we're doing research methods, we need to understand how we're going to define research in order to understand what methods are relevant when talking about research. So if we look it up in the dictionary, we find out that it says a systematic and unbiased way of solving a problem by answering questions or supporting hypotheses through generating verifiable data. So quite often when we look things up in the dictionary like this, instead of having one word we don't know, we now have multiple words we don't know. So what is systematic? What is unbiased? What is a hypothesis? And what do we mean by verifiable? So these are all very important questions which we will come back to later on. So for now, we just need to recognize that research is a good way of solving a problem through generating useful data. That's probably a simple enough version to get us started. So that then begs the question, why would we use research methods to solve a problem? Clearly, there are many other ways to solve a problem. So why would we use research, or why would we not use research methods to solve a problem? So this is a question so fundamental that we don't always ask it. So let's think a little bit about other possibilities. How else might we solve a problem? We might rely on authority, for example. So when you were younger, you probably relied on your parents. You would ask your parents, what do I do about so-and-so? How do I solve this problem? Or now you're in Hong Kong, perhaps you go and ask your supervisor. You expect your supervisor to help you solve at least some of your research problems, if not your personal problems. And in extreme situations, you might even go and ask the police to help. Now in Hong Kong at the moment, the trust in the police is not so great, so many young people would not be willing to ask the police for help, but there are times when we all do need to ask for the police to help us solve a problem. So how else might we do it? Personal experience. So for example, I've tried doing this before and I know that it worked, so it should work if I do this again. Common sense. Common sense in English means we apply simple logic. In other words, if it's very clear that A causes B, then clearly in those situations we might not need to do research in order to find out whether A causes B. It may be so obvious using simple logic. Revelation. Revelation means you rely on your God to tell you. So it could be a Christian God or a Buddhist deity. It doesn't really matter what the religion is. You're basically saying religion and your God is how you solve a problem. Or intuition. So intuition means we rely on our instincts or on our feelings. Okay, so all of these, we probably have used all of these at least in some time in the past, and we often don't even really think very deeply about when we use these different solutions. And that may change over time. So for example, my children are now probably both about the same age as most of you. So my children would very rarely rely on my authority anymore to tell them what to do and what not to do. So in English, there is a joke that when your children are very young, they think their parents know everything, right? So a small child thinks their parents know everything. And then when children become teenagers, they think their parents know nothing. In other words, they're resistant to any advice from parents. And then when their children become young adults, the joke is they're amazed at how much their parents have learned. Now, of course, it's not that their parents really have learned something, but now they're willing and able to recognize that actually their parents do know quite a lot. So the parents may not know everything, and they may think their parents' knowledge is out of date, but they still recognize that their parents do have a lot more life experience, and that may be helpful in solving certain problems. Okay, so I've listed here 4 possible problems that we can think about in order to understand how research compares with the alternatives. The first one is, should I cross the road at a specific place where there is no pedestrian crossing? Secondly, what should the Hong Kong government do to improve air quality in the next 20 years? Thirdly, who should I marry? Not me personally, but maybe for all of you to think about if you're not married. And then fourthly, should I become a Christian or a Buddhist? Now I'm going to discuss all 4 of these, but normally I would ask everybody in the classroom whether they think research is a good way to solve each of these 4 problems. I don't have the opportunity to do that when we're doing a video, so I would encourage you all to stop the video now and think for yourself about whether you think research is a good way to solve each of these 4 problems before you carry on watching the video and hear what I have to say. You don't have to necessarily agree with me, but at least I would like you to think about your own answers first. So, first of all, crossing the road at a specific place. So, when I go home from work, I often drive down Sassoon Road, which is the road where the student halls are near to the Queen Mary Hospital. And what always amazes me, although there's a pedestrian crossing, there are many people who cross near to the pedestrian crossing but don't use the pedestrian crossing. So for educated young people, you would think this is a rather silly thing to do, right? It's obvious that there is a crossing you can use, which is clearly should be safer, so why not use the crossing? But this question is rather the other way around. If there is no pedestrian crossing nearby, should you cross the road? Okay, so is it good to use research? So obviously, if we're talking about the broader question about safety at crossings which are not marked, you may think it's obvious it's not very safe. But in fact, it does seem appealing in one way to use research because it's something where we may not know the answer, right? And clearly this could be a matter of life or death. So you could think it's an important enough question to do research. So why wouldn't we use research here? And I would argue the primary reason is time. In other words, the whole reason why someone crosses the road where there's no crossing is because they don't want to spend the extra time to go to a place where there is a crossing. Now sometimes that's honestly because there is no pedestrian crossing anywhere nearby. Sometimes it's just we're lazy, we don't want to make the extra effort to walk the extra distance or walk up the steps to the bridge. So the whole issue then is to actually answer this question using research at that particular point would take a long time, right? You would have to collect data, watch people who cross the road and see how dangerous or how safe that experience is. So you might be standing there for months in order to reach the conclusion whether it's safe or not, when in fact by the end of those few months the situation may have changed. So your research is no longer very useful. So this doesn't seem like a situation where we would use research. Generally we would use common sense, such as, is there a safe alternative? Can we actually see far enough in each direction to see whether we can cross the road before a truck comes along and knocks us over? Right, so there are some places where it's clearly very unsafe because we can't see very far and because there are lots of vehicles at high speed perhaps. Right, so those are all things where we might argue actually common sense should tell you what the safety is. Okay. Let's think about the second problem. What should the Hong Kong government do to improve air quality in the next 20 years? Now, if I asked you the question about whether we should use research here, most people would say the answer is yes. But it's not immediately obvious why the answer is yes, perhaps. So let's think about why the answer might be yes. So first of all, is this an important problem? I think most of us would agree this is an important problem. It affects the health of everybody living in Hong Kong. And for some people, it could be even a matter of life and death. If you're somebody who is an asthmatic, for example, this could really be very serious for you. Okay, so it's an important problem. What about the resources? Do we have the resources? Well, clearly, although the government at the moment is claiming that they're short of money because they've been handing out money to address the virus, the Hong Kong government still has a large amount of financial reserves. Most governments around the world actually have debt primarily, and their debt far exceeds their resources on any reasonable calculation. But the Hong Kong government, that's not the case. Even leaving aside the value of all the buildings in Hong Kong and of the land, just the direct financial resources already are so substantial, they clearly could afford to spend money on this. And then lastly, the time horizon, right? We're talking about the next 20 years, so it doesn't matter really that much if it takes us a year to do the research, if this is going to be useful for the next 19 years after that. Okay? And also, there's an issue of transparency. In other words, we have to persuade people that this is a good use of public money. So having some good evidence that we can show everybody is also very important. So, in other words, people may not trust the government too much, but at least if the government can present evidence, say that, academics at Hong Kong U or Chinese U or somewhere else have done this research, then there's likely to be a higher degree of trust that the policy is well founded. It's based on good evidence. Okay, what about the third problem? Who should I marry? Now you might say, this is a bizarre sort of question to ask in the context of research. So let's just think about it. So is whom you choose to marry an important question? Well, for most people it is. Now, of course, if you've decided you're never going to get married, maybe this question is irrelevant to you. Or maybe you would like to get married, but legally you can't. So if you wanted to marry someone of the same sex, same gender in Hong Kong, you can't currently do that legally in Hong Kong. Of course, you could always go overseas, so you might argue this is an irrelevant question for me. But for most people, this is one of the most important decisions we all make in our lives. So it's not that it's not important, and most of us would be willing to invest quite a lot of time and effort in making that right decision. So the question is research a reasonable way to solve this? So what's the problem with research? Well, it sort of depends on how you define the scope of the research. So if research means I'm going to marry a sequence of people, say 10 different people, and then at the end I will decide which of those 10 people was the best person to be married to, clearly this is not likely to work. Because if it turns out that of the 10 people you've married, it's the first one who actually was the most suitable person for you to marry, they've probably married somebody else in the meantime, and they probably don't want to marry you again because they're probably very angry with you for having divorced them in the first place. Right? So that doesn't seem to work. So what are the other alternatives? Well, historically, people would ask often their family for advice, right? So I don't know if any of you watched, there was a series on Netflix recently about Indian families and their use of people to help them find someone suitable to marry. And so this is quite interesting because it's talking about people your age or a little bit older. Generally, it was people who hadn't been able to find a suitable partner and they felt it might be helpful to have help. But the context of that TV series was that often it was the mother of the young man or the young woman who was basically telling them who was or who was not suitable. So even they had this other woman trying to give them advice, it was actually essentially a negotiation between the young person and their parents, and to some extent with input from this advisor. So, but the difference was that most of the young people wouldn't allow their parents to tell them who to marry, but they were willing to accept suggestions, at least, as to whom they would marry, but they still, most of them, still wanted to make the decision themselves. Okay, so you could argue in some sense the research was being done by this person who was trying to give them the advice about whom to marry rather than themselves, And then at the last stage, they would go out on a series of dates with this person and see whether things worked out well. Okay, so that's who I should marry. Now, what about the last one? Should I become a Christian or a Buddhist? In other words, how should I choose a religion? So this is clearly, again, for most people, a very important question. Although, again, one could argue that there is another choice here, which is not to have a religion at all. Some people might want to be atheist, which means I don't believe in any God. Some people might just be agnostic, meaning I don't particularly want to spend my time worrying about whether there's a God. I just don't think this is important. Right? So that would be, if you like, one of the choices. But if you think about a choice like that, it does seem a little bit strange that we don't use research very often. Right? So the reality is that most people, their religion comes from either their parents or from their schooling. So in Hong Kong in particular, schooling has turned out to be very important. So our current chief executive and the previous chief executive are both Roman Catholics. So they both go to Roman Catholic Church. And the interesting thing to me was that they both became Roman Catholics not because of their parents, but because of the school they went to. So in Hong Kong, traditionally, many religions set up schools. And of course, that benefits the community in a sense. You've got somebody willing to set up a school as an alternative to a government school. But essentially, they have the ulterior motive. So there's some Catholics who are very famous for saying, if you give us a child until the age of 11, they will be ours for life, meaning we will be able to get them into our religion. So in practice, it's actually linked back to what choice the parents made about which school to send their children to in many ways, rather than anybody doing research. Okay, so what's the conclusion to all of this? So you don't necessarily have to agree with my conclusion, but my argument would be that all of these methods that I listed above may all be useful at times. So if you believe in religion, usually you would believe that your religion should be helpful sometimes. If you're educated, you would usually believe that common sense is sometimes useful. When you're younger in particular, you would believe that relying on your parents' advice may be very useful sometimes. And as academics, you clearly believe that research is useful, at least in some contexts. So the key point, I think, is that we believe that research is a good way to provide good long-term solutions to important problems. Long-term, because it will take us time to find the answer. Important, because we have to invest usually time and money. And good ways is because we have an inherent belief that research works well in finding solutions. Okay, so let's come on to the next little element, which is one of the words in the definition of research was verifiable, or sometimes people use the word testable. So what's the context for this? So clearly in all research, it's important that other researchers can try to replicate your findings, meaning if they do the similar research to you, they should reach a similar conclusion. So if you're an experimental scientist, you usually would talk about this as being a repeatable experiment. That means researchers should provide enough details when they report their research that other people should be able to replicate their findings by repeating their experiment. So this can be a little bit difficult in situations where people want to patent certain of those ideas. So something like CRISPR, which is the technology for gene modification, for example, has been patented. So this can be quite tricky, right? How do we deal with this potential conflict between people wanting to make money out of their knowledge and wanting their experiments to be repeatable? Right? So generally, I would argue that replication is a crucial part, right? At least you need to allow people to know enough that they can check and see whether they can get similar findings to you. Okay, that's okay if you're doing experimental science, but what if you're dealing with research that cannot be repeated? So, for example, if you were interested in the return of sovereignty in Hong Kong, or the handover, whatever you want to call it, clearly there's a problem, right? We can't replicate what happened in 1997 in Hong Kong. We can't replicate it in Hong Kong, and it's difficult even to find a close analogy elsewhere. The closest we can probably easily find is Macau, where Macau, we had in 2000, we also had the return of sovereignty to the mainland. But Macau was a return of sovereignty from a different country. Portugal had a quite different relationship with Macau to the British relationship with Hong Kong. So, for example, Portugal and Britain both joined the European Union. If you were a Macau citizen before 2000, you were automatically a Portuguese citizen and hence an EU citizen, whereas the British took a different approach. So there were quite different contexts for the return of sovereignty in Macau and Hong Kong, and both of those have gone by. It's already 20 years since the return of sovereignty in Macau, so it's quite hard to replicate those findings, right? We can't repeat the experiment. What can we do? Well, at least we can reanalyze data that people collected before the return of sovereignty. And of course, we can collect new data now, but it's quite hard to do a comparison to data from before 1997 unless it happened that somebody already asked those questions and is willing to give us access to the data set. So this means that high quality data collection is particularly important for non-experimental situations, or at least situations where some of the data cannot be collected experimentally. So for social science is one quite obvious one. The social conditions have changed, but there are many other disciplines where data collection can be extremely expensive or difficult to repeat. So for example, astronomers who are studying the creation of stars, you can't go back and say, oh, please redo that black hole being created or that star being created. Right? Again, if the data wasn't collected before, it's too late. Or indeed, if you're a geologist studying volcanoes, we can't control when the volcanic eruptions occur. So some volcanoes erupt quite frequently, but many volcanoes might only erupt once in a lifetime. So it may be very hard to collect historical data to compare with the current situation. So this also explains why, particularly in the US and Europe, research funded with public money must share the data, and journals nowadays often require public access to any data analyzed in a journal paper. So I'm old enough that I still remember having an argument with the editor of a journal in statistics because somebody had published a paper. I believed their analysis was faulty, but they refused to give me access to the data set that they had analyzed in their paper. And the journal editor said, sorry, there's nothing I can do about it, because the journal at that time did not have a policy that required that you must give some access to the data sets for papers that you publish in that journal. So in fact, this is one of the things which has changed relatively recently in Hong Kong U. So for all of you, if you are collecting or generating data sets, you will need to deposit your data set with Hong Kong U. There is not yet a requirement that you must share your data, but at least you must deposit the data in case there are any questions about the generation or collection of your data. And I would argue that good scientific process should be that you should be willing to share your data with others after you have done your own analysis. Okay, now the whole context for research is, the reality is, as human beings, we all make mistakes. We all have some false preconceptions, and the argument behind this says that society and the state of knowledge can only advance if mistakes can be identified and corrected, which is at least in theory possible with research because people can check the findings for mistakes. So indeed, this is one of the arguments you could have democracy. So I don't want to, this is, if you like, my one political statement in this course. There's a famous statement that democracy is a terrible form of government, but it's better than the alternatives. So arguably, the logic behind this is that if the representative you choose in a democracy is ineffective, you can try a different representative in the next election. Right, so that's, I would argue, the core underpinning argument for democracy. Okay, so in other words, you're able to correct your mistakes. You're not stuck with them for the rest of your life. Okay, so let's say a little bit about research plan. Okay, so the reason I want to talk about research plans is because we're going to say a little bit about which parts of the research plan are relevant for this course and which parts are not. So after you've chosen a research topic, usually your research plan contains at least most of the following elements. So the first thing is you would be expected to do a literature review, which is basically answering the question, what do we already know about this topic? Okay. Now sometimes that can be quite hard, sometimes it can be quite easy. It can be quite hard in a situation where a particular subject has been researched by different disciplines, and sometimes people in the different disciplines don't read the literature of each other. So you may get very different perspectives about a problem from different disciplines, and it's not clear how to synthesize the findings from those different pieces of the literature. Okay, the next issue is the research design, which is essentially an overview of the methodological decisions taken. So we are going to talk about some of the methodological decisions. We are going to say something about research design. We're primarily going to talk about quantitative research designs, although I have a chapter in the book which also covers qualitative research, even though I'm assuming that most of you in this group will not be doing any qualitative research. The next core element is sample and population, which means we have to define the population that we are studying and also how we are selecting our sample from that population. So we will talk about both population definitions and how to draw a sample from a population. That's a core element of most research plans. The next element is what in this course we will call operationalization. So what is operationalization? Operationalization is saying what measuring instruments are we going to use in this research. So we need to be able to describe the measuring instruments, and we need to be able to test those measuring instruments to see that they work well. So we're going to talk about reliability and validity. Pre-test basically means we need to check that the instruments work before we use them. So sometimes those instruments have been developed by other people and there's already enough good literature about them that we don't need to do much testing of the instruments. But there are other situations where that may not be the case, either because the instruments are new, or maybe we're using instruments in a slightly different context than people have used them in the past, so we need to show that they work in our context. So we're going to talk about that in some detail. Data collection, we are going to say something about that, although not a lot. We're basically not too interested in the detailed mechanics, but we're going to see how data collection, some aspects of it are important for data quality. Data analysis is the last part of this course, but maybe in some ways the core. So the last, at least the last week or two of this course, we will be focusing on data analysis. We will talk a little bit about presentation, but not very much, and a little bit about how to interpret those results. We're not going to talk about work schedule. We're not going to talk about dissemination. The draft instrument basically means if you're creating your own instrument, you need to provide the details. And then ethical approval. So I used to chair the Ethics Approval Committee for non-clinical research in Hong Kong U. If you are dealing with human subjects or vertebrate animal subjects, you would normally need ethical approval, and this is something that your supervisor should be advising you on, and you need to obtain that ethical approval before you start data collection. And then lastly, bibliography. We're not going to talk about this in this course. I would simply point out that EndNote, which is a very useful bibliographic tool, is free in Hong Kong U, and the library offers free courses in how to use it. So I would strongly, if you don't know about EndNote, I would strongly encourage you to learn how to use it and make good use of it. It will make your bibliographic part of your thesis much easier. So as I've summarized here, we're going to focus primarily on research design, sample and population, operationalization, the basics of data analysis, and presentation of results in this course. I also teach a practical data analysis course in second semester. So that's a hands-on course. Hopefully, assuming we're going to be able to run it in the classroom, it will be run in the statistics department lab. If not, we will run it using Zoom in a small group. So what we're going to talk about from now on is what's sometimes called the scientific method of research, including both qualitative and quantitative methods, although I will only mention the qualitative part in passing. So these methods are used across a wide range of disciplines. It's not just used in STEM disciplines, it's also used in the social sciences, it's used in education, and it's used also to a large extent in the some parts of the arts and humanities as well. So, if we're going to use the scientific method, then we need to talk about what the scientific method is. So if we look up the scientific method in the dictionary, this is defined as an objective, logical, and systematic method of analysis of phenomena devised to permit the accumulation of reliable knowledge. So let's look at the last part first. Clearly we want a method which permits the accumulation of reliable knowledge, right? We don't want to accumulate unreliable knowledge. So then we have to look at the other part. So phenomena just means things that we have observed. We may or may not be able to measure them directly, but at least there will be some form of measurement possible. So we're also going to have to talk about what is objective, logical, and systematic. So as I've said, phenomena are what we observed. We may not be able to measure directly. In fact, there are many things which we can't measure directly. Something as basic as temperature, we actually can't measure directly usually. We're usually measuring indirectly. Brain measurements, for example, have the potential, in principle, to change our understanding of human behavior. But in general, a lot of what we study in human behavior is by observation or by self-report from the human beings. So some of that may be subjective, particularly if it's a self-report, my attitudes or my feelings. Some of it is relative objective, so time and weight measurements. Okay, so what is objective? So if you look up objective in the dictionary, it says objective means to evaluate phenomena from a dispassionate, apolitical, atheological, and non-ideological viewpoint. So that sounds really quite difficult. Can we really evaluate something with no passion, no politics, no religion, and no ideology? Right? That's a real struggle. So I will never forget when I was a grad student, about the same age as most of you, and my funding body in the UK sent me off to a weekend course with other grad students. And the intention of this weekend course was to prepare us for the big bad world after grad school. The assumption was that most of us would not become academics, So we needed to be prepared for the world and becoming employees. And I met some other people on the train who were going to the same place. And we were sitting on the train having a very intense argument about some of the issues that we're going to talk about today in this course. And we were in a part of the train, there was maybe, I think, 6 of us sitting together having this very intense discussion. And there were 2 other people who were not part of our group. And one of them looked over at us and said, "Are you all researchers?" And we said, "Yes." She said, "At university?" And we said, "Yes." She said, "Oh, I'll make sure my children don't ever do that." Right, so she was very put off by our intense discussion. We were being very passionate about what we believed in and what we thought were the right ways to do things and the wrong ways. But this says we need to evaluate without passion. But we need to recognize here the key here is objectivity in evaluation. In other words, when we are evaluating the things that we observe and measure, that's where we need to evaluate without passion, politics, religion, or ideology. So this is when we're testing the ideas and reporting our findings, this has nothing to do with choosing the research problem. So indeed, if you have no passion for your research topic, your life will be really quite boring, right? What keeps you going if you don't find your research topic interesting? Now, maybe you didn't have any say really in your research topic at the moment because it was chosen by your supervisor, but at least the general subject area, I hope you have some passion for it if you intend to spend a considerable amount of time, if not the rest of your life, studying that particular area. So again, hopefully you have some passion for your research problem, your research domain, but to be good researchers, we need to evaluate things from this dispassionate, apolitical, atheological, and non-ideological viewpoint. Now, I want to make a clear distinction here between ethical and unethical evaluation. So unethical evaluation is evaluation which tries to distort the evaluation for whatever reason. So some people distort the evaluation because they are in a hurry. They don't want to make the effort, or sometimes they distort it because they're not honest. So without being political, I think you can see we have a leader in another country, Donald Trump, who basically has stated publicly he downplayed the virus because he didn't want to scare people. Right? So he understated how serious the virus was as a threat to life. And I think most people would argue that clearly was a very bad idea. So maybe people didn't get scared enough in order to change their behavior. Right? So, but that's one issue. I mean, that's one form of ethical concern. But even our ethics as a researcher, right? Clearly, here we're not focusing on unethical evaluation. We're talking about evaluation which does not intend to distort, but it's possible for it to be distorted simply because we allow our preconceptions to influence how we do the analysis. So you all either have taken or will be taking a research ethics course which does address those issues. But I am not here going to talk about unethical evaluation. So that raises some rather deep philosophical questions. Can you, as a scientist, truly be objective? And can the process be truly objective? So the honest thing is we need to sometimes reflect on that, because asking a question can sometimes alter the views of the respondents. And I don't just mean intentional. In other words, asking questions in a way to try and downplay people's views is one issue. That's clearly unethical. But sometimes asking the question can affect the respondent views in ways that are not always so obvious unless we give some careful thought. And even if you're a physicist, right, in a quantum experiment, we know in that context that measurement affects the thing you're trying to measure. So I have a social science example. So previously, So the centre I look after does contract research for other people around the university. Some of them we do the full research component. Sometimes we just do the data collection and then hand over the data to the other researchers in order for them to analyze it. So we were commissioned by a colleague who was in the Department of Social Work and Social Administration, and he was interested in the issue about elderly people in Hong Kong retiring to the mainland. Okay? And so this was at a relatively early stage in the discussion of policy, and so the government wanted to know whether elderly people were even discussing with their family members this possibility. So in the survey, one of the core questions was asking elderly people, have you discussed with your family members this possibility? So if the answer is no, what do you think they will do after the survey is finished? So what actually happened here was, when you do a survey, you always do some checking on the quality of the survey. So in a telephone survey, that normally means that for some of the telephone calls, you will select randomly some to call back and check the answers. So you get somebody else to call back. So what happened was that my fieldwork staff came to me very concerned. They said, we're doing callbacks in this survey, and usually in the callback, we do basic demographics to make sure we've got the right person in the household, and then one or two core questions to make sure that those questions were being properly asked during the survey. And they said, when we call back, the answers to the question are quite different. So I was saying to them, you think about it, imagine you're an elderly person. So one of the things about telephone surveys and elderly people is that most people, you call them up, they don't really want to answer your questions over the telephone because they're busy. But for elderly people, sometimes they're a bit bored. So as long as the questions are not too boring, all about money, but if the question's about something interesting and personal, they often are quite interesting and quite happy to answer your questions. In fact, the problem can sometimes be they don't want to stop. They want to keep telling you things. So I said, imagine that you're an elderly person. You've been on the phone for 15 or 20 minutes doing a telephone survey, and you put the phone down. And let's say there is another family member present. Let's say it's your son or your daughter. If you've been on the phone for quite a long time, they're likely to say to you, oh, that was a long phone call. Who were you talking to? And they would say, oh, it was someone from Hong Kong U asking me, have I ever discussed with you the possibility of retirement in the mainland? Okay, so what do you think will happen next? So clearly, if they've already had that discussion, then it's not very interesting. But if they haven't had that discussion before, that very act of asking them the questions is likely to put the thought in their mind that they probably will think about discussing that topic with their family members. Right? So this is why we need to be very careful. The survey in itself can bias the process if we're not very careful. Right? So, in fact, it's not perhaps such a serious matter, given that this is something the government wanted to happen anyway. But it does mean we need to be very careful. If we ask those people again, their answers will have been influenced by the previous data collection. So let me give you a second example. So this one has become very relevant again, because this example is during SARS. So during SARS, I don't know if you know that in Hong Kong, SARS was particularly serious in one particular housing estate, a place called Amoy Gardens. And there was one block in Amoy Gardens where many people got infected. So everybody who lived in those blocks was put into quarantine, but the government didn't have enough quarantine facilities to quarantine everybody in the whole estate. So they only quarantined the ones that they believed lived close enough, i.e. in the same building, that there was a real risk. Because in fact, it was quite clear there must have been some chain of infection within the building, and there was a long argument about how that infection occurred. Right, so spreading of SARS was a little different to the spreading of COVID, but there was some similarity. So the government asked us to call up everybody who lived in Amoy Gardens in a telephone survey and ask them about their personal hygiene behavior. So obviously at that time the issue was not masks, but it was things such as, after you sneeze, do you wash your hands? After you go to the toilet, do you wash your hands? When you're sharing a meal, do you use serving chopsticks, or do you just use your own chopsticks to share the food? So the first time we did the survey, no problem, right? Everybody was happy to answer the questions. But then 2 weeks later, the government said, we want you to do the survey again. And I said to them, I'm a little bit concerned about this because we told people that this was just a piece of research. But actually, if we call back again after such a short period of time, they will wonder whether we're actually really checking up on them. And indeed, that probably was at least part of the reason the government wanted to ask these people again. Right? They basically wanted to see whether the public information notices were having an effect, but specifically on people in this particular housing estate. So I said to them, you realize some people are going to get a little irritated, so we need to be quite careful how we explain this to people when we do the survey. So anyway, we did the second survey, and some people did indeed refuse, but most people consented a second time. And then another 2 weeks later, the government said, we want you to do it again. And I said, I think this is a real problem because this will be interventional research, not observational research, which is what we told people we were doing. And indeed, I was proven correct that nearly everybody refused to answer the phone survey the third time. They basically said, you're clearly, chasing me. I don't trust you that you're not going to come and knock on my door and say, why aren't you doing this? And indeed, in those situations, many people are not going to answer the questions honestly. They're going to tell you what they think you want to hear. So, of course, they're going to tell you that they're behaving perfectly, even if they're not. So the trust breaks down then between the researcher and the population. Okay, my third example of where this can be tricky is what's called publication bias. So we know very well that the academic process as a whole has some bias in it. So for example, if you have some findings which are very different to the current mainstream thought, some people will reject your research and say, we have already got all this literature showing that this other method or this other way of thinking about the problem is the right way to do things. Right? We don't need to suddenly do what you are proposing and your ideas. We don't need your ideas. We already have a good explanation for this phenomenon. On the other hand, there may be some very open-minded people who will look at it and say, oh, this is wonderful. You've got a new idea. We must publish it, even if, frankly, the idea is not very good. Right? So we know that there is bias in this process of selection of papers. And in fact, there is some attempt to try and address this. So I'll just give you one example. So for example, clinical trials for drugs. So clinical trials for drugs, or for example, vaccine. Let's make it more relevant, vaccine. So clinical trials for vaccines or drugs now have to be pre-registered in most countries. Pre-registered means I have to record with the government that I'm starting to do this study. Why? Because the worry is that when we get to the end, if it turns out that our vaccine doesn't work very well, so let's say we've tried this vaccine in Hong Kong, we've tried it in America, and we've tried it in Europe. And it works very well in Europe and America, but not very well in Hong Kong, because in Hong Kong there are side effects. then there would be a temptation for the drug company or the vaccine company not to report the Hong Kong findings, only to report the findings that are positive. Right? So in order to avoid this, you're normally required to pre-register it, and the results must be made public at the end. And indeed, there are some researchers who believe all research should be pre-registered to avoid this bias. So this is a little bit tricky, because when research doesn't get published, that can be for a number of different reasons. It could be because the research basically just confirms the existing knowledge, which actually is important if we believe in replication, but it's not very interesting to most journals. Or it could be that it doesn't get published because, frankly, the model that you're trying to use or the analysis you're doing are very poor. Now, it's not necessary that the question is wrong, or that even the research data is faulty, but just simply you don't know how to analyze it properly. So we have to be careful, right? There are clearly biases in the process that we need to be aware of. Okay, so let's move on to the next issue here. I said that in addition, we also needed to use a logical and systematic method. So what does logical and systematic mean? So logical reasoning means we need to follow the rational rules of induction and deduction. So this is philosophy, but these are the basics of philosophy which as researchers we all need to understand. So what are deduction and induction? Deduction means we start out with a general theory and we apply it to a specific situation. In other words, this is the type of research where we're trying to test existing theories in new situations, looking for a situation where the theory fails. Okay? So the honest truth is that's what a lot of people spend their time on in research, right? Because we may not be smart enough to think of a new and better theory, so we're trying to find the weaknesses in the theory that already exist. So this is what people often talk about when they talk about the scientific method. But we also need to recognize the other side, which is induction, which is going from the specific to the general. In other words, for example, if I'm dealing with a situation where either there is no theory existing, or the theories that are out there are already known not to work very well, at least in some situations, then I'm trying to come up with a new theory, to generate a new theory that works better than the existing theories. Right? So anytime deduction leads me to the conclusion that a theory fails, I need something to replace that theory with. So this is one of my little stories. So when I first came to Hong Kong U, they had a general rule that all new chair professors were supposed to give a public lecture. So the idea was, if somebody is an expert, right, which they should be to be a chair professor, they should be able to give some form of public talk which is interesting to the general population. Now, of course, for some people whose work is very theoretical, that may be a little bit more difficult. But at least in principle, there should be something interesting, even if it doesn't have any obvious applications. So we had a gentleman who was the chair professor of physics. And he'd been in Hong Kong U, I think, 5 to 10 years, and he'd somehow managed to avoid giving his public lecture. So he waited till 1 week before he left Hong Kong U to give his public lecture. So I suspect he was giving this lecture under protest. In other words, he really didn't want to give it. So I don't think he took it too seriously. Because one of the things he said in his lecture was, physicists are the only true scientists because they rely entirely on deduction. Okay, so that's a rather strange thing to say. Okay, because he said they don't make the mistake of using induction. Now, in fact, why is this particularly amusing? It's particularly amusing if you think about the example of Einstein. So the amazing thing about Einstein is that he's famous for coming up with not just one theory, but at least two major new theories. Right, so the theory of relativity was induction. Right, he took the weaknesses that were already known to occur in Newtonian laws and found this new theory, which not only explained all the things that Newton explained, but explained things that Newton couldn't explain. So in fact, I think it was just last year, I don't know if any of you saw, one of the implications of some of Einstein's work was about something called gravitational waves. And it suddenly got to the point, I think it was either last year or the previous year, where someone was able to show for the first time that Einstein's predictions of one of the implications of gravitational waves was correct. Because nobody had previously had instruments which were good enough to be able to show that his predictions were better than the traditional predictions. And they finally managed to do it. So this to me is true brilliance. This is true genius, right? That you come up with a new theory which not only is able to cover everything which the old theory worked, but it also covers new domains which the existing theory doesn't work with. So anyway, clearly induction is just as important as deduction. Okay, so that's one side, that's the logical part, but what is systematic? So systematic method means a procedure for doing things that can be explained to others and is built on previously existing knowledge. So both of these are very important. So the literature review is supposed to be able to show that what we're doing is built on the previously existing knowledge, even if we're able to show that some of the existing knowledge has weaknesses, right? But at least nobody is starting from ground zero. We're starting from a lot of existing knowledge as our starting point. Now, explain to others. So this is generally why we write journal articles and books. The whole point is that coming up with a great new theory is one thing, but you're not going to have much influence if nobody else knows what you've done or if they don't understand it. Now, the interesting thing to me is that often a lot of mathematicians, for example, come up with some wonderful new theories, but they often themselves have little idea about how to apply those ideas. So it may take, for example, a theoretical physicist to take the mathematician's ideas and turn it in the first level of application and turn it into a physical theory. It may then take a material scientist to then make use of that in terms of understanding its implications for materials, and it might then take somebody in electronic engineering to see, oh yes, I can create some new semiconductor as a result of this. So it could take several stages to where the rest of science understands that idea. So it may be that not too many people understand that idea originally, but at least in principle, we need to be able to explain that idea using some form of language. Now, of course, amongst mathematicians, if you're using some highly abstract mathematical concepts, maybe not too many people understand it, but at least hopefully some other mathematicians should understand it. So again, the key point is if nobody can understand your ideas, then clearly they cannot evaluate it either. So we also need to talk about analysis. So what exactly do we mean by analysis? So in general, analysis means both qualitative and quantitative methods of processing and summarizing information. So we do need to say a little bit about qualitative and quantitative methods. So for now, let me just start by talking about what quantitative methods are. And then later on, I will take you briefly to say what's different about qualitative methods. We'll see that qualitative methods often have quite a different philosophical underpinning. It's not just the method of analysis that's different in the direct sense, but the whole conceptual framework. So within quantitative analysis, I'm proposing here a relatively simple hierarchy about the levels of quantitative analysis. So the first level is what I'm calling descriptive. So I still remember receiving a journal article review back which said, this is a very interesting paper, but unfortunately it only includes descriptive analysis. So this was meant to be a very negative statement, meaning you don't have any model here, so you haven't led to any understanding of this phenomena. But actually, accurate descriptions are sometimes really important as the first stage before we go on to doing deeper quantitative analysis. So what's the sort of thing we're thinking about? Well, for example, simple statistics relate the description of the sample to the description of the population. How good is that description? So we're going to talk later on about how close our sample results are to the population. That's indeed a core element of what we're going to talk about later on. But even if you've collected a very large sample, there still can be issues about the analysis. So for example, population size. So the government just released new predictions of the population size in Hong Kong for the next 50 years, I think. So this is clearly very important because if we want to know how much housing we need in Hong Kong, clearly we need to know how many people are going to live here. If we want to know how many schools we need in Hong Kong, clearly we need to know how many people of school age there are going to be in Hong Kong. So these sorts of descriptive analysis are really important in terms of planning for the government, right? So a lot of the analysis done by the Census and Statistics Department can be criticized by academics as being purely descriptive, but actually those descriptions are really important, although one can argue that descriptive alone may not be enough. So let's talk about the next level of analysis in my hierarchy, and this is what I call explanatory analysis. So explanatory analysis means we want to try and understand why things happen as they do. We want to try and understand how reliable is that understanding. And we also then, of course, want to know whether there might be other possible explanations. So, for example, if the government says that the unemployment rate has gone up, as it actually has done for the last few months, we want to understand why has it gone up. So is it because of the virus? Is it because of it's getting to the end of the year and there are young people entering the labor market? Is it because restaurants are sacking dishwashers and replacing them with machines? So in all of these situations, we usually need statistical models to try and help us to understand what the possible explanations are and how they might help us to lead to a policy initiative, right? So these situations, statistical models are really invaluable in this sort of situation. And we will talk in some detail about these sort of models later on. And then the third and final level in my hierarchy is predictive. In other words, what if we want to make a model of future outcomes and we want to understand how well would it work? For example, if we are looking at admissions to universities, can we predict which students will receive admissions offers before they get their public exam results if we know their performance in school exams? Okay? So in fact, as I said, I've been in Hong Kong U a long time, and actually I've been at least partially involved with admissions for a long time. So in fact, if anybody who has any parents who have teenage children meet me and they find out that I work in Hong Kong U, if they were to find out that I have anything to do with admissions, they will often ask me a question. So if we were face to face, I would ask you what questions you think they might ask. So as you might have gathered from this, one obvious question they will ask me is my child likely to get admission to Hong Kong U to study, and then usually it's law or medicine, might be business, not too often other disciplines, because that's usually not so hard to get in. Right? Could be actuarial science. I think that's the third most difficult to get in. And so the honest answer is, I don't know. I don't know whether your child is likely to get in because, number one, I don't know how well your child will do in the exams, which are the primary issue in Hong Kong U generally. And number two, getting admission depends on your performance relative to all your peers, all the other students in the same cohort trying to get admissions. So in other words, if I want to know how many school students will get admitted to study social science each year, it's very easy because we know how many places we have. So I can say we have so many places for a Bachelor in Social Science, so many places for a Bachelor of Science, so many places for Bachelor of Arts, and so on. Right? But beyond that, it depends on the performance of each particular student relative to the other students. So that's actually a very hard prediction for an individual student because it depends on the ability of that student, it depends on how well they do in exams, and it depends, of course, how well they do on that particular day when the exam is held. So maybe on the day that the exam was held, they weren't feeling well, they found it difficult to concentrate, so the performance was below expectation. So in fact, if you've been following what's happened in the UK this year, they had a big fuss because the government was trying to work out performance without having the exams. So they were initially taking the school-based results and tried to do some scaling of the school-based results to decide who should get which grades. The problem is how to do that adjustment. And in the end, the government was forced to admit that the adjustment process wasn't very fair, and so they allowed students to get admitted on the basis of the predicted grades from their school. So one of the problems with that is that the predicted grades usually are an overestimate if you average across the whole population. So it meant that suddenly the students had higher grades than expected. And in the UK, they give conditional acceptance, whereas in Hong Kong, we do it all after the grades are announced. So if everybody in Hong Kong got one grade higher, it would make no difference to the admissions process because it would just mean that it's harder for everyone, right? Because the cutoff would go up one grade. Okay, so anyway, predictive models are generally much harder because we're generally dealing with individuals rather than the population as a whole. So because of variability from individual to individual, those are generally much harder to deal with. So let me just give you one simple example. If, for example, you're dealing with biomedical research and you compare a study that someone's done on rats and a study that someone does on humans. So when you explain that to the general public, they just assume that the major issue is that rats and humans are different, which is of course true. But one of the other issues is that laboratory rats have been bred to be genetically identical, whereas human beings are very different. It'd be like saying, in the human study, we only study people who are identical twins. Clearly then, the human beings would be much more similar. But we have enormous genetic variability of human beings across the world. So it's actually quite hard in dealing research with human beings. On the other extreme, if you're a physical scientist and you're dealing with what? Blocks of metal, usually you can create those blocks of metal to be extremely similar. So the variation from block to block should be very limited compared to the things which people who are dealing with biological processes have to deal with. Okay, so prediction in that context may be easier because the individuals are all relatively similar. Okay, two other core concepts that we need to talk about. What is a theory and what is a model? So a theory, if we look it up in the dictionary, it says a generalized synthetic explanatory statement. So that's not really a very helpful definition. I prefer the second one, an abstract conceptual explanation of the world. So clearly, conceptual explanations are important in order that we can generalize our findings across a wide range of situations. But we need to connect those conceptual explanations to the real world through predictions. So how do we get a prediction so that we can test our theories? For that, we need a model. So a model is the way to generate verifiable predictions, so that word verifiable again, based on a theory. Although in finding that model, there may be uncertainty involved, and there may also be unknown parameters for the model that we need to estimate in our research. So let's take an example. Let's say our theory says increased education leads to increased personal income. Okay? That's a very clear theory, but actually it doesn't enable a prediction, because I don't know how increased education leads to increased personal income. So for example, if our model predicted that personal incomes increase proportionally to the years of education, we still need to know the slope and the intercept of that linear relationship before we can make predictions, and we still need to know how much uncertainty is left over. In other words, how much variability there is even after we know the years of education. So we need statistical models to estimate those parameters, given there is also uncertainty, as these are not exact models. So in fact, this also relates to a piece of research I did in the past. I was looking at what's called in Hong Kong the one-way permit scheme, which is the way that Hong Kong controls people who have family connections to Hong Kong coming from the mainland to Hong Kong. So for part of that study, one of the things I needed to do was to understand the connection between education and personal income. So I wasn't using the years of education, but the level of education. So people who only had primary education or less, lower secondary, upper secondary, post-secondary, first degree, master's degree, PhD. Okay? And so I did not want to assume how education related to personal income. And so I actually looked at the census data. So that's a very big sample. That's 10% of the whole population, in order to try and understand how that worked. And I found that, with one exception, as you went up a level of education, so the average personal income went up. So my question to you is, can you guess what was the one exception to that rule? So I will pause for a minute for you to think about that. So again, I would normally ask this in the classroom, and the answer, of course, is PhD. Because many people who have a master's degree, it's a professional master's, and so those people are earning quite high incomes in the private sector. Most PhDs in Hong Kong, or a lot of PhDs, work in academia. Academia is not poorly paid in Hong Kong, to be honest, but it's certainly not paid at the same sort of level as people who have commercial jobs in the private sectors with master's degree. So we can see very clearly what that connection is. Okay, so the key point here is a theory is of little value until it is testable. In other words, we should be able to build a model that can be empirically tested. If that model fails, then we will need to modify our theory, or at least the way that we convert that theory into a model. But what we need to recognize is, if the model does not fail, it does not mean that the theory is correct. It suggests the model may be useful if and until we're able to find a test that the model fails. So of course that begs the question, what do we mean by a model fails. We mean that there is some inconsistency between what the model predicts and what happens. So we will examine later on how to use statistical testing to identify a model failure. So clearly, a theory that leads to models that allows us to make good predictions is a useful theory, but we should not assume that it is necessarily a fundamental truth about the world. So the classic example, as I mentioned before, is Newton and Einstein. So in fact, for many centuries, people thought that Newton's laws were a fundamental truth given by God, until Einstein showed that some of them fail under certain conditions. So if you are traveling at speeds close to the speed of light, then some of Newton's laws do not work. But you will notice we still use Newton's laws every day despite Einstein's findings, because they're so close to being true at everyday speeds. So unless you happen to have a very fast car that can travel close to the speed of light, which I don't think will happen with any of our lifetimes, then we don't need to worry too much. So for most situations, we can still happily use Newton's laws, even though we know some of them are actually untrue. So in short, while absolute truth may exist, we will never know whether we have found it yet using the scientific method. So a famous statistician, George Box, once said, "All models are wrong, but some are useful." Right? So all models are wrong, but some are useful. In other words, all models have some imperfections, but that's a separate issue from whether they're useful for us to use them in daily life. Okay? Now, I mentioned at the beginning this word hypothesis. So what actually is a hypothesis? So a hypothesis is a statement that can be empirically tested. It's a translation of a theory into a testable statement, which can happen, of course, through a model. Note that a research question may be as specific as, do young people protest more than older people? Which links to the hypothesis, the young people protest more than older people. Or maybe even a broader question, such as, why do Hong Kong people protest? Which doesn't link it clearly to any hypothesis, right? Because there's all sorts of possible reasons that such a broad hypothesis is not something we can easily test. Now, within hypotheses, we generally, when we're trying to test them, divide them into two types. The research or alternative hypothesis is a positive statement about what the researcher expects to find, such as young people protest more than older people. The null hypothesis is a statement that a relationship expected in the research hypothesis does not exist. In other words, that the world is simpler than predicted by that theory, such as there is no difference in how much younger and older people protest. Or another example would be, let's consider the proportion of males and females studying undergraduate degrees in the whole of Hong Kong U. The simplest explanation would be that there should be no difference, right? There are roughly the same proportions of males and females in schools, so why shouldn't there be roughly the same proportion of males and females studying in the whole of Hong Kong U? So this might be my null hypothesis, the simpler one, but actually I don't really expect it to be equal. I would expect it to be unequal because we know there are some biases in society. So this might be my research hypothesis. Now, research papers do not always explicitly state the hypotheses, but if they're testing, for example, whether there is a relationship between education and income, there is an implicit null hypothesis that there is no relationship between education and income, and the implicit research hypothesis is that there is a relationship, and it may actually go beyond that to say what that relationship actually is. this does beg a question. Why do I think the hypothesis of equal proportions is simpler? So this actually yields two questions. First of all, what is simple? And secondly, why do I care about simplicity? Or even, I guess there's maybe even a third question, why do I think simplicity is a good thing? Okay, so that's actually turns out to be a rather deep philosophical question. So this question, or this philosophical idea, is sometimes called Occam's principle, or Occam's law, or even Occam's razor. And in fact, there was nobody called Occam. His name was actually William of Occam, and he was a medieval philosopher, meaning he lived many centuries ago, so he didn't write in modern English. So this is an attempt to turn his statement into modern English. So we can quote his principle as meaning, if we have two explanations of the world which are equally good in predicting outcomes, we should prefer the simpler explanation. Okay, so whether the two explanations are equally good, that's actually a statistical question that we will talk about later. But we haven't really, this doesn't really tell us what simpler is. But the core question here is, first, why do we prefer simple explanations? So rather than me trying to tell you why I think we should prefer, I decided I would try and look at some famous philosophers to see what they said. So Karl Popper is probably the most famous philosopher of science who ever lived. And Karl Popper said, we prefer simpler theories to more complex ones because their empirical content is greater and because they are better testable. So their empirical content is greater, meaning we rely less on the theory and more on what the data is telling us. Why they're better testable? Well, because the simpler the theory is, we should be more easily able to disprove it, right? So, okay, that sort of explains it, although it's maybe not that obvious. So let me look at some other philosophers. So Richard Swinburne is a famous modern philosopher of science. The way he said it is like this. Either science is irrational in the way it judges theories and predictions probable, or the principle of simplicity is a fundamental, synthetic, a priori truth. In other words, either we've all been wasting our time as scientists, or this is fundamental. Well, this to me is extremely unhelpful. It's basically saying either we're all idiots, or we should just accept this, which makes absolutely no sense to me at all. I mean, there's no logic then as to why should this be a fundamental truth. So Ludwig Wittgenstein was probably even more famous as a philosopher than Karl Popper, but not really a science. But he also talked about Occam's principle. He said, Occam's principle is, of course, not an arbitrary rule, nor one justified by its practical success. So I find that sentence very funny. And I mean in the sense of laughable, because whenever anybody says is, of course, not something, means I actually don't have a good reason. But I'm just trying to bluff you, right? So it's not an arbitrary rule. Well, but actually Richard Swinburne has just said it is an arbitrary rule. He's also said, so this is a philosopher, nor one justified by its practical success, right? So only a philosopher would say practical success tells us nothing. Most of us would say if something works very well over a long period of time, we generally would think that must be a pretty good idea, right? So unless we have a better idea, if this one's worked for a long time very well, then we would generally think that's a good idea. But he's a philosopher, right? Philosophers don't care about practice. The next part, though, is a little bit more interesting. He says it simply says that unnecessary elements in a symbolism mean nothing. So this one to me is actually quite interesting. He's basically saying, if I've got two models which are equally good at predicting, that says there's something redundant in the more complex one. So that I agree. You're basically saying, if I've got two explanations, one simpler than the other, there must be something redundant in the more complicated one, which tells me nothing really. So then he says, signs that serve one purpose are logically equivalent, signs that serve no purpose are logically meaningless. So again, the last part is basically saying, if I don't need something, then it's logically meaningless. And then finally, he basically restates Occam's principle in an interesting way. He says the procedure of induction, so he's basically turning Occam's principle into what induction means. He's saying induction means, in effect, if we accept Occam's principle, that we should accept as true the simplest law that can be reconciled with our experience. Okay? In other words, the simplest law that gives me good predictions, or the best predictions I've got so far, that should be the one that I accept at this stage. Obviously, that may change in future because I may find a better law that can produce better predictions of my experience. So Wittgenstein to me is very interesting, as I said, all the way from philosophical gobbledygook, which is how I see the first sentence, to the end, which I find very helpful because he's basically telling us, in my view, how we can use Occam's principle when we're doing induction. So we start with the simplest possible model and work our way up until we find the simplest model, which is good enough in explaining what we can observe. So let me just give you one extreme example. So the extreme example says the world is predetermined. So if the world is predetermined, that means, for example, where every atomic particle is at any time from the beginning of time to the end of time is predetermined. So that is a mind-boggling complex hypothesis, right? That basically means however many 10 to however many watt power of atomic particles we have, however much you want to divide up time into, what's the smallest increment of time we can ever observe, that's how many combinations of, and space. So we've got all the different possible locations in space of all the particles at all points in time. So that's unbelievably complex, number one. Number two, it is of zero value in predicting the future, because if everything's predetermined, then the past tells me nothing about the future. So that clearly is a useless theory in our consideration. Okay, now we're going to come later on to statistical models, and in fact I'm going to ask you in this week's assignment to look generally at statistical models. So for most statistical models, we expect the null hypothesis to be rejected, and hence the alternative hypothesis to be the tenable or believable one. So thus they're usually complementary, and the null hypothesis is usually the simplest statement. In other words, what Occam's law is saying is we will keep the null hypothesis unless we can find evidence that says, no, the research hypothesis provides better predictions than the null one. Right? We will talk about that in much more detail later on. So if a paper uses statistical methods, there must be a null hypothesis and a research hypothesis, even if they're not clearly stated. But notice that this whole process here is not symmetrical. We can only disprove hypotheses, we cannot prove them. So generally we're looking to see if there is evidence to disprove the null hypothesis, and if we can't find sufficient evidence, we will just accept the null hypothesis and not move on. It's only if we are able to show enough evidence then we will reject the null hypothesis. Now we have to be careful here because strictly speaking, statistics cannot usually even disprove a hypothesis, because all we can usually show is that the outcome we observed was very unlikely compared to the outcomes if the null hypothesis is true. This is because statistics uses probability statements, and usually all we are able to say is that the chance of observing this particular outcome, if the null hypothesis is true, is so small, if the null is true, that we cannot accept that relative to the alternative hypothesis, the research hypothesis. So we're usually prepared to reject the null hypothesis as unlikely to be true if there is sufficient empirical evidence against it. And we will come back later to the question of what is sufficient evidence. So for example, let's take a very simple case. I toss a coin, right? Now, of course, in a classroom, I could actually toss the coin for you, but I'm not going to toss it. But let's say I've tossed a coin 20 times, and every time I get a head. Would you believe me that this is a fair coin, meaning it has one head and one tail, which are equally likely? Probably not, right? The reason is because if it is a fair coin, the chance of getting 20 heads in a row is about 1 in a million. On the other hand, if my coin has 2 heads, it's a certainty that I will get 20 heads in a row. So clearly it's much more likely that I'm cheating with a 2-headed coin than I'm unbelievably lucky. Right? If I was really somebody who could easily show you outcomes which only happen 1 in a million, then clearly I would be an unbelievably lucky person. Now, of course, if I do 1 million experiments and then just choose the one where I'm successful, then you would say I'm cheating, right? So we need to be very careful. How many times have I done the experiment? But if I've only done it once, then the chance of 1 in a million just seems too small to believe that the null hypothesis is likely to be true. What about simplicity? So I'm sort of going to wave my hands around a little bit here. We will talk about this a little bit later on when we come to the statistical models. Often we define simplicity in terms of the number of parameters in our statistical model, meaning the smaller the number of parameters in our statistical model, then the simpler that model is. The more parameters, the more complex. Sometimes we look at it the other way around. We say the sample size minus the number of parameters in our model, which is sometimes called the degrees of freedom. So simplicity would mean either that the number of parameters is small or that degrees of freedom is large. So if the degrees of freedom are large, that means the number of parameters is small compared to the number of data points. Okay, we're getting near the end of the chapter. So proof and verification. So what exactly is proof? Proof means I know the truth for certain. So mathematical proof, which is something we don't deal with in this course, yes, if I believe that I'm using a particular system of numbers and logic, I can prove that if A is true, then B must be true. Right? Those are things I can prove using the theory of logic and using certain assumptions about how numbers and set theory work. Verification. So what is the real difference between verification and proof? So many people think that verification is proof, but it's not. Verification means we did not disprove the truth. Okay, so what does that mean? So for example, let's say if I want to know whether who you are who you say you are, can I prove your identity? Probably not. Right? How would I prove your identity? I probably can't. I might be able to prove it arguably if I took a DNA sample from you and your parents. So that at least would allow me to prove whether you are actually the child of your parents. But of course, you could be a different child from the one that you claim to be. Right? I have no easy way to know. Verification, however, means my test did not disprove the truth. Now, clearly, even if you were all in the classroom and I wanted to take the register to see who's present, I'm not going to ask for DNA samples for you to prove who you say you are. I generally just accept that people sign their initials against my list. So that's a very weak form of verification, because I don't even know what your signature should look like. So a stronger form of verification would be, I ask you to show me your student ID card, and I check that the picture matches you, which is fine, of course, unless you've done something drastic to your hair since you had your ID card photo taken, right? Or I might ask to see your passport photo, because I might think the passport is more trustable than a student ID card. So if your picture matches your face, that means I have verified your identity, but it's not proof. You could have an identical twin. You could have a fake document, right? There are a number of possibilities. So it's not proof, but it's verification. So if you test many hypotheses resulting from a theory and none of them are shown to be false, you may think the theory is true because of numerous verifications, but you have not proven it. You have verified it. It could be that the weaknesses in the theory have not been identified yet. Again, we come back to Newton's laws and the theory of relativity. Okay, what else do we need to deal with? We need to talk about random variables. So what are random variables? Well, first of all, a constant, when we talk about a research design, a constant is something that we assume does not vary over our study and hence cannot explain anything that varies across the study. So for example, your gender, we would assume usually that your gender would not change within a study. If the study only covers a short period of time, we would assume that we can treat your age as a constant, right? As long as the period of time we take is small enough. So those would be things we would assume constant because they're not going to be an explanation. On the other hand, if we did a study that lasted 3 years, then actually your change in age could be an explanation of some of the things we see in the study. So that would not be reasonable to assume your age is constant. So conversely, a random variable is something that varies within the study. So it could be that it varies over time. It could be that it varies over the subjects of the study. But we also use random variable to mean how we have defined a concept operationally, meaning how do we measure something, this thing that's varying. So creating a good operational definition is a skill, and it's important to have done your literature review to see how people measured this thing. And we're going to talk about operational definitions in a later chapter, including how we know whether we have a good operational definition. So for here, we're more interested in the issue that random variables vary over time or over the subjects in our study. So amongst these random variables, first of all, the most important ones are the explanatory variables. So what are the explanatory variables? They are the random variables that are the object of the research, meaning these are the variables that you can find in the research hypothesis. So my previous example about education and income would mean that education and income are clearly my explanatory variables. Those are the two variables which are the focus of my research and are related to my research hypothesis. Now, within explanatory variables, we divide them into two types. So this division is a rather arbitrary decision because it assumes that we can divide up our random variables into the causes and the effects. So that may be an oversimplification because some variables can be both a cause and an effect. But usually within a particular hypothesis, there is a cause and an effect. Okay? So the independent variables are the presumed causes, the dependent variables are the presumed effects. Okay? So that means that the null and the research hypotheses must be describable in terms of the dependent and independent variables. The simplest situation would be that the research hypothesis is that the independent variables affect the dependent variables, and at least one null hypothesis is that the independent variables do not affect the dependent variables. Of course, if you have multiple independent variables, then you may have a more complex situation because you've got more than two hypotheses of interest. So if there are no independent variables, then the hypotheses must be describable in terms of the dependent variables only. So that is possible. Okay, so that seems simple, but unfortunately it's not, because there are many other variables around. Not just the explanatory variables, there may be other variables which are also varying within the study. So the extraneous variables are the random variables which are not the objects of research. So first of all, we have what we call confounding variables. Confounding variables means these are extraneous variables that are related to the independent variables. So we will see later on that that might be a problem. So what we often try to do is to control these extraneous variables, meaning we want to exclude their effect on the relationship between the independent and dependent variables. So there's two different sorts of ways we can remove the effect of the extraneous variables, either through manipulation or by including them in a statistical model. So we will talk about that in a minute. We may also have control variables in order to try and reduce the variability. So even if we don't think these extraneous variables are connected to the research hypothesis, they may be things that we can use to reduce variability, such as, for example, genetics. We might believe that genetics has nothing to do with the independent and dependent variables, but within genetic groups, people are relatively similar. So we might control for genetics in order to try and reduce the variability. Now, what about the rest of the extraneous variables? So uncontrolled variables means extraneous variables that have not been controlled, which we are generally assuming to be irrelevant. In other words, we're generally hoping they don't play any role in the research. So clearly the research is at risk if the variables we assume are irrelevant are indeed confounding variables. So that means it's very important that in stating our research problem, we give careful thought to the variables in our study. In practice, there's limits to how many variables we can control for, so at least we need to ensure that we control for those with the largest potential effect. So controlling is basically an attempt to exclude the effects of variables that are not of research interest. Okay? Now, the mechanisms of control, first of all, manipulation means these mechanisms of control. The simplest mechanism is one category. That means all the subjects have the same value of the controlling variable. So let's say I'm interested, again, my example of education and income, and I decide I don't have enough resources to study the whole population, so I'm only going to study males, or I'm only going to study females. Okay? That clearly makes it simpler because I don't have to worry about the effect of gender. But the disadvantage is I cannot generalize my findings. So if I've only studied males, I have no idea whether the same results would show up if I studied females. Okay? But as a first step, that may be a reasonable thing to do, particularly if it turned out that only males there was a big problem. So the next stage is what we call a block control. That would mean I include the males and the females separately, so I don't need to assume that there is the same pattern within males and within females. I'm going to study males and I'm going to study females as well. So this is a good approach if I only have a few blocks to consider and I believe that the blocks might be very different. But if I have multiple controlling variables, my problem is my block size may get too small. The block size means how many subjects per block. So if I started out with a sample of 100, but if I had 10 blocks, then I only would have 10 subjects per block. Right? That might be too few for my analysis. That might not be enough for me to do a decent statistical analysis. So that may not be practicable. We can also sometimes do randomization to remove the effects. So in a medical treatment, we often would randomize to different treatments. So that's allocating subjects to groups using chance. So this assumes that assignment choice is possible. So if I have, say, 3 different medical treatments, in order to avoid bias, I could randomly allocate my subjects to the 3 different treatments, so that hopefully the advantage is then my 3 groups should be similar not only on the things I've controlled for, but on all the variables I've assumed irrelevant. So randomization is a very powerful tool if it is both possible and ethical to do random allocation. Now, of course, there are times that's not possible. So, for example, if my treatment, if you like, is smoking or non-smoking, clearly I cannot ethically ask anybody to smoke. So I could not randomly allocate people to a smoking or non-smoking treatment situation anymore, given that we know how harmful smoking is to human health. So randomization, again, may be tricky for ethical reasons or because it's simply impracticable to do the allocation. Paired control. So paired control is a form of randomization. This would mean, for example, if I had 2 treatments, I would pair my subjects to be similar within the pairing. So the idea would be, for example, let's say I believe that the most important thing to control for was severity of my disease. So I'm doing a drug intervention. So I would pair all my individuals from the pair who had the least severe all the way up to the pair who had the most severe. And then within each pair, I randomly allocate to the 2 treatments. So that way, I'm trying to make sure that the severity of disease is a fair comparison between the 2 treatments. Because if I just did it subjectively, whichever of the treatments I thought was more likely to be good is likely the one I would give to the more seriously ill people. That would clearly introduce bias in the whole evaluation process. Now, statistical control means I try to control for things which I cannot do through allocation, but by assuming that by including in my statistical model, I can completely remove the effect. So that's not a bad objective, but it can be very difficult to use statistical controls in practice in a very good way. So what's the problem? The primary problem is one of measurement error. So the problem is then with all these control mechanisms, and particularly the one of statistical models, is that there may be errors in the measurement of the controlling variables. So I've got an example here which we will talk about in some detail. So this is a study about passive smoking. So what had happened is that we had got to the stage in science where everybody except the tobacco companies fully accepted that smoking was a serious risk to health. The most obvious risk is lung cancer, but also many other forms of risk, including heart disease. So everybody accepted that smoking was a major risk to health. The question was, what about passive smoking? So passive smoking means I don't smoke a cigarette or a pipe, but I'm around other people who do smoke cigarettes or pipes. So I breathe in the smoke that they have breathed out. Okay, so the question was, how do we assess that? So the first two major studies that looked at passive smoking were based on studies which were household based. So the logic went like this. If we compare non-smoking women with non-smoking husbands to non-smoking women with smoking husbands, okay? So if both a husband and wife are non-smoking, their exposure to cigarette smoke at home will be generally low. I mean, it's still possible if there are other family members who smoke, but at least they won't be getting it from the partner whom they presumably spend most time with in the household. There might also be work exposure, but let's leave that aside for now. On the other hand, if you have a non-smoking woman who has a smoking husband, then that means she should have a risk of getting lung cancer because of breathing in her smoking husband's passive smoke. And then if the woman smokes, then clearly in that situation we can see the risk of her smoking herself, right? That will be the primary risk. So the idea was that by doing this comparison of this study of looking at smoking and non-smoking husbands and wives, we should be able to understand passive smoking risks. Now, it was primarily non-smoking women with smoking husbands because it was relatively rare to have a smoking woman who had a non-smoking husband. Now, why? So the issue was that there was a lot of social prejudice in those days. So this is the 1960s and 70s. In those days, generally it was not considered socially acceptable for women to smoke, but it was socially acceptable for men to smoke. Okay? So that's why it was primarily looking at the passive smoking effect on women from their husbands. So what was the problem with this study? The problem was that they didn't account for measurement error. Right? So what's the measurement error? The measurement error is that people lie about smoking. Okay, so let's think about this for a minute. So it's true, you could have lying amongst both the men and the women. So you could have men who are non-smokers lying and saying, I'm a smoker when they're not. But actually, when you think about it, that's not very likely to occur, right? It might occur, but it's not very likely. What was much more likely to occur is that women who were actually smokers, but hiding it from their husbands, would not admit to being smokers. So some of the women who claimed to be non-smokers were actually smokers. So that's one component. But again, if there was bias in both directions, you might think that should balance out perhaps. But unfortunately, no. Because think about when you go to visit somebody in their home where somebody in the household is a smoker. So when you go into their home, how would you know that there is a smoker? Right? So normally, again, I would ask the class to tell me. So one obvious way is you see ashtrays around the house. Okay, that would be one way you know there are smokers in the household. But even if there was no ashtrays in the house, what would be another way to know whether anybody in the household smokes? So this is not so obvious in Hong Kong because many people in Hong Kong, because of the high humidity, do not have wallpaper on their walls. But in many colder countries, when you go into their house, you can smell if somebody smokes. Because the cigarette smoke gets stuck in all the furniture, it gets stuck in all the wallpaper, so when you walk in, even if nobody is smoking, at this time, you can smell that somebody has been smoking there. So, in other words, it's quite hard to hide being a smoker in a non-smoking household, but it's quite easy to hide being a smoker in a smoking household. You think about it, right? So let's say the husband is a smoker and the wife claims not to be, but is a smoker. So if the husband goes out and she wants to smoke, first of all, she can leave the windows open. Secondly, You know, if the husband smells cigarette smoke, you can say, oh no, that's leftover from yesterday when you were smoking. And of course, she can also steal some of her husband's cigarettes, or if the husband finds a pack of cigarettes, as long as she uses the same brand as his, then she'll say, oh no, I think that's your pack that you forgot from before. Right? So it's much easier to hide your lying if you are married to a smoker. So if it turns out, if you put these two things together, first of all, that people who are smokers are more likely to lie than people who are non-smokers. And secondly, people who are married to smokers are more likely to lie than people who are not. Those two things together created bias, and it meant that the risk that was assumed to be due to passive smoking, some of that risk was due to the fact that these women actually were smokers, not just breathing in their husband's passive smoking. Now we realize this problem, we can take account of it. We can do, for example, urine or hair sample tests to check how much people smoke. Right? So there are ways of checking now to see whether people are telling the truth, and we can take even account of the fact that people lie in our models. We can account for that measurement error. So the problem was simply that we hadn't taken account of the measurement error in the early models. Now, as I mentioned, controlling methods that rely on allocation are only feasible, A, if we can do the allocation, and B, there is not an ethical problem with the allocation. We may also have problems that the control variables may also interact. So how do we deal with some of these problems? So in addition to pure statistical controls, there is one approach called propensity scoring. I'm not going to talk about this in detail, but this is one way to handle situations where the allocation is non-random. We can look for potential bias by looking at the probability that someone will be treated given their explanatory variables. So this is what's called a propensity score. So we can get estimated effects of the treatment that are not biased by the measured explanatory variables. So I've given you here a reference to a paper. So I don't have time to talk about this in great detail. There is still some argument going on in the literature about how useful propensity scoring is, but it's clearly better than making no adjustment at all for non-random allocation. Now, this whole issue of research and null hypothesis, dependent, independent, and control variables, I want to give you one very nice example. So this is a 1950 paper by Sir Richard Doll and Sir Austin Bradford Hill in the British Medical Journal. So this is the most important paper in the history of research on smoking and lung cancer. So this is not passive smoking. This is on the direct effect of smoking on lung cancer. So this was a purely epidemiological study. In other words, it was not based on knowing the biological processes. This was based on the statistical evidence, trying to see whether there was evidence to support that smoking was linked to lung cancer. So what did they do? They had tables that showed the numbers of lung cancer or control. So what did they use as a control? So their control was hospital patients, other hospital patients, matched by gender, age, and hospital. So they recognized that the pattern of people going into different hospitals was different. They recognized that lung cancer, like many other cancers, is much higher in older people. And they also took into account gender in case that gender was part of the story as well. So they have lung cancer or control by gender and smoking or not. So the research hypothesis here is that smoking is associated with lung cancer. The null hypothesis is that there is no association. Lung cancer or not is the dependent variable. Smoking or not is the independent variable, while gender, age, and hospital are the control variables. So remember, Whether a random variable is an independent variable or a control variable, it cannot be in both, may not be obvious without looking carefully at the research hypothesis, because they were including gender, age, and hospital in their model, right? But they were assuming that those were control variables because they're not mentioned in the research hypothesis. It's not their focus. Their focus is, in fact, is smoking a potential cause for lung cancer? Right, so the independent variable is included in the research hypothesis, but the control variables are not. Okay? Now, one last little thing for those of you who are biological scientists. There are other methods of randomization other than through allocation. There's also what's called Mendelian randomization. So Mendelian was a botanist. So he discovered that when he crossed purebred white flowers and purebred purple flower pea plants, the result was not a blend. Instead, all the offspring were purple. However, when he self-fertilized those F1 generation purple flowers, he obtained purple flowers to white flowers in the next generation in a ratio of 3:1. So that suggests that genes for different traits are passed independently of one another from parents to offspring. So many of you know far more about genetics than I do, but for those of you who don't, this is one of the core principles of genetics. So what does that mean? It means that actually nature is doing randomization for us. So if we're interested in individual genotypes and parental genotypes, we can use that random assignment that occurs before conception to make causal influences, assuming that the genotype is associated with the exposure of interest and is independent of the genotype from our confounding factors and from the outcome after we control for the exposure and confounding factors. So the strength of this is it does not rely on our allocation process. If you like, nature is doing the allocation for us. So there are some situations where we cannot use, if you like, Mendelian randomization, or if you like, prefer God's randomization, or conceptual fertilization in the sense of conception. Right? These are all different ways that we could look at this. So the conditions for using Mendelian randomization are quite restrictive, but it does mean there are some situations where we can use this to understand the causal processes which are going on. Okay? So that brings us to the end of chapter 1 and the end of this video. I hope you have found this chapter interesting. Please make sure that you first do the feedback assignment in Moodle based on chapter 1, and then you will also need to do assignment 1, which is based on the materials of chapter 1. That is for grading. That is what you need to send to me through Moodle, but again, it's grading only in the sense of pass failure. And when you're ready to look at assignment 1, please download the materials for assignment 1 from Moodle, and also make sure you watch the video about assignment 1 before you continue. And then later on you can come back and watch the video for assignment 2. Okay? Thank you very much.